NASA says that Voyager 1 has become the first man-made object to reach interstellar space.
But we really had no idea how big the solar bubble is. Now we know.
NASA's Voyager 1, launched almost 5 decades ago, has made a startling revelation that sends shivers through the scientific community. Far beyond its expected lifespan, this intrepid explorer, now billions of miles away from its launch pad, continues to transmit data using technology the like of a vintage cassette player. The groundbreaking mission, initiated in 1977, has uncovered a shocking discovery from the last frontier, captivating the world's attention. What did it encounter beyond the heliosphere? Did it signal potential alien intelligence? Or was it a cosmic disaster looming for Earth? Join us as we unravel how Voyager 1 just turned back and made a terrifying discovery. The epic journey from Mariner to Voyager. In the spring of 1965, as humanity prepared for the first manned missions of the Gemini project, a forward-thinking supervisor named Joe Cutting at JPL's Advanced Projects Group led a team. Their goal was to explore potential outer planet missions and upcoming launch opportunities thoroughly. A decade after the International Geophysical Year, the United States, having lost the robotic moon race to the Soviet Union, was now turning its attention to lunar exploration and space dominance through a well-funded, manned program. While unmanned exploration in the 1960s set the stage for later Apollo missions, the idea of flights to distant planets fascinated minds almost as much as the Apollo missions themselves. Exploring other planets became the logical progression of unmanned exploration programs. Looking back, there's often an overemphasis on the perceived scientific focus of unmanned missions compared to the political and technological goals of manned flights. Despite arguments favoring robotic missions for their scientific purity, it was the promise of planetary photographs that captured the public's imagination and fueled unmanned exploration during the golden age of spaceflight. In this context, the United States and the Soviet Union entered a new phase in their celestial competition, a race to the planets. The turning point came in 1962 when the American mission Mariner 2 reached Venus, marking the Soviet Union's first loss in the space race. Fast forward to 1965, when Gary Flandreau and his colleagues, part of Joe Cutting's team, were assigned to study future opportunities for missions to the outer planets. It seemed like the next logical step in a space race, gaining momentum each year. However, the challenge was securing enough rocket power for the unmanned program to explore outer planets, a whole new challenge. Consider a solar system with planets orbiting a central star. The closer planets, influenced more by the star's gravity, orbit faster, while the more distant ones, with greater circumferences and less gravitational pull, orbit more slowly. Interplanetary travel depends on minimizing fuel consumption, considering gravity and velocity in trajectory planning. Now, think about a unique scenario: a planetary gravity assist. Imagine taking advantage of windows from Earth to Venus, and by the time you reach Venus, another window opens to Mercury. Using Venus's gravity, you can precisely bend your trajectory toward Mercury, minimizing the need for a major engine burn. This concept laid the groundwork for the successful Mariner 10 mission in 1973, highlighting the importance of intermediate planetary gravity assists. The theoretical groundwork for these innovations had roots in the works of pioneers like German rocket engineer Kraft Erika and astronomers like Hugues Lovehie from the Copernican age. Flandreau's predictions, based on historical trends and planetary positions, revealed a once-in-every-176-year occurrence, a quadruple convergence of all 4 gas giants in the 1980s. This alignment became the genesis of the Grand Tour, a groundbreaking concept revolutionizing outer planet exploration. However, in 1971, the 4-planet mission concept faced official rejection. NASA approved the Mariner-Jupiter-Saturn project in 1972, a series of 2 flights to the 5th and 6th planets. Despite officially downsizing to a 4-year mission, within JPL, a culture of persistence and optimism emerged. Engineers envisioned spacecraft designed not just for Saturn, but with the potential for further encounters with Uranus and Neptune, completing the grand tour in 12 years rather than the initially proposed 30 years. Despite NASA's slow embrace of the grand tour, the Voyager mission began to take shape. In 1977, the approval of Voyager marked a pivotal moment in the ongoing saga of space exploration. Can the pursuit of the unknown truly have an end, or does it propel us into an ever-expanding future that transcends the bounds of our imagination? The Voyager twins race through the solar system. On August 4, 1977, precisely at noon, NASA released the official press kit for the groundbreaking Voyager missions. These interstellar pioneers were set to embark on a monumental journey atop the Titan IIIe rocket, also known as the Titan Centaur. This colossal launch vehicle, featuring a cryogenic upper stage, stood in sharp contrast to the Titan IIs that previously launched the Gemini capsules into orbit. Capable of lifting an impressive 15,500 kilograms to low Earth orbit, the Titan Centaur had previously launched the Viking Mars landers in 1975. Within the press kit, NASA revealed a tantalizing possibility, an additional objective for Voyager 2. The spacecraft could potentially chart a course for Uranus, adding a tertiary mission to its already ambitious itinerary. Voyager 2, scheduled to launch first at the end of August, could, if fortunate enough, barely catch the old Grand Tour window originally envisioned by Gary Flandreau. An encounter with Uranus could become a reality, provided Voyager 2 remains healthy after its Saturn flyby. Meanwhile, Voyager 1, set to launch 2 weeks later, opted for a more fuel-efficient and shorter route to Jupiter. Despite its later launch date, Voyager 1 was poised to reach Jupiter 4 months ahead of its companion, Voyager 2. During encapsulation, someone recounted being the last person to physically touch the spacecraft. Concerns about fragile instrument windows prompted a meticulous inspection, ensuring the telescopic windows were snug, each given a gentle twist for good measure. The 2 Voyagers, bound for Saturn, would journey in tandem, yet arrive at the ringed giant 9 months apart. The contingency plan was clear. Should Voyager 1 face setbacks in achieving its Saturn objectives, Voyager 2 could be rerouted to cover those goals. A compromise was struck, allowing Voyager 2 to serve as a backup, ensuring the success of the mission's primary objectives. If, however, Voyager 1 succeeded in all aspects, Voyager 2 held the option of a less valuable Saturn flyby, opening up the potential for a meeting with Uranus. Uranus took center stage in the Voyager press kit, mentioned 19 times, while Neptune remained visibly absent from the narrative. Yet, for those privy to the intricacies of the mission, Neptune quietly positioned itself where it needed to be, ready to step into the planetary spotlight should the decision be made to extend Voyager 2's celestial journey. Officially, however, the press kit maintained a silence on anything resembling the original Grand Tour idea. What lies beyond the known realms of our solar system remained a tantalizing mystery, waiting to unfold with each passing celestial revelation. In total, 3 Voyager spacecraft were constructed and assigned serial numbers. However, only 2 were initially intended for launch. The third served as a partial spacecraft, primarily as a source of backup parts in case of any insurmountable pre-launch system failures. Less than a month before the scheduled launch, failures in 2 of the 3 onboard computers of Voyager 2 prompted an impromptu switch. The spacecraft, originally designated as Voyager 1, was moved up to the earlier launch slot and subsequently flew as Voyager 2. This decision provided NASA and JPL approximately 2 weeks to address the issues with the malfunctioning computers. Adding to the complexity, the physical spacecraft themselves were switched at the last minute to facilitate repairs. Additionally, NASA had to swap the radioisotope thermoelectric generators to ensure functionality. The Titan Centaur's dance with destiny. Given that the Voyager 2 probe had to ensure the possibility of continuing its mission beyond Saturn, one of the two sets of radioisotope thermoelectric generators was overclocked to extend its guaranteed electrical output life. Despite complications and changes in the launch order, the mission was approved for an on-time launch. 2 years after the Viking mission to Mars, precisely at 10 hours, 29 minutes, and 45 seconds a.m. Eastern Daylight Time, the Titan Centaur's 2 large solid rocket boosters were ignited, marking a point of no return. The program progressed according to the schedule. The vehicle exhibited normal responses, with only minor attitude disturbances of 1.2. The combined weight of the rocket, spacecraft, and fuel was 1.4 million pounds, slightly over 635,000 kilograms. The 2 solid rocket boosters, constituting Stage 0, provided almost double the thrust of the entire vehicle during the initial powered flight phase. Guidance data affirmed that we were on the correct trajectory. For 117 seconds, the boosters burned, releasing combustion products from a mixture of powdered aluminum fuel and ammonium perchlorate oxidizer, bonded in a polymer known as P-band. 10 seconds before jettisoning the solid motors, the 2 LR-87 liquid engines of the core stage were initiated in mid-air using a small solid rocket motor start cartridge. The solid rocket motors were then shut down. 4 minutes and 20 seconds after the launch, staging occurred, and the LR-91 single engine ignited, propelling the spacecraft higher, faster, and farther into orbit. 8 minutes after launch, just before entering orbit, the LR-91 ran out of fuel as planned. At this stage, the primary propulsion comes from the Centaur high-energy upper stage, which remains hidden within the fairing, along with the payload during launch. The Centaur stage differs from the preceding stages, utilizing 2 RL-10 cryogenic hydrolox engines. Similar to the old Atlas rockets of the Mercury program, the Centaur is a balloon tank, deriving structural integrity from the internal pressure of its fuels. Its thin walls contribute to an excellent energy-to-weight ratio. The Centaur initially burned to position itself and the Voyager spacecraft into Earth orbit. 42 minutes later, just half of one orbit around Earth, it fired again, imparting such incredible speed that even Earth's gravity couldn't hold it back. Voyager 2 was now en route. An hour after launch, approximately 12 minutes after the second Centaur burn, the Voyager spacecraft separated from the upper stage. Attached to the bottom of Voyager was a kick motor, officially called the propulsion unit. This represented the final boost for Voyager's outbound trajectory. As a solid stage, it couldn't be shut down or throttled, and provided a guaranteed velocity increase of 2,000 meters per second, or 4,500 miles per hour. To prevent Voyager from exceeding its intended speed, the Centaur was deliberately cut off ahead of schedule. As the propulsion unit executed its final boost, Voyager was precisely positioned. Attitude control during the last 43-second kick was maintained by 4 externally mounted reaction control system pods, drawing fuel from the main hydrazine tank within the Voyager bus. Upon separation of the Star 37E solid motor, having fulfilled its mission, it took these RCS pods with it. Voyager itself featured 16 smaller hydrazine maneuvering thrusters, primarily for attitude control and minor mid-course corrections. The ability of Voyager to alter its trajectory became restricted, carrying 105 kilograms of hydrazine fuel for its reaction control system thrusters, pressurized with inert helium gas at 420 psi. 2 weeks transpired as Voyager 2 embarked on its extended journey towards Jupiter. Meanwhile, Voyager 1 underwent significant developments. The flight data computer was successfully repaired and reinstalled, but the guidance computer proved irreparable. Instead, it was substituted with the one from the third backup Voyager spacecraft, initially a proof test model not intended for flight. Voyager's autonomous navigation in the depths of space. On September 5, 1977, Voyager 1 joined its sibling, commencing its journey toward Jupiter. The boost phase of Voyager 1 proved to be a critical moment. The LR-91 stage of the Titan III burned for a shorter duration than intended, placing a heavier load on the liquid hydrogen Centaur stage. This resulted in the consumption of 1,200 more pounds of precious hydrolox fuel than planned. During the second Centaur cutoff, it was estimated that the stage was possibly as close as 3.4 seconds away from total propellant exhaustion. If a similar failure had occurred on Voyager 2, with its more fuel-demanding flight profile, the Centaur might have run out of propellant before the probe reached the proper trajectory, and the solid rocket motor would have been unable to compensate. Fortunately, JPL and NASA narrowly averted disaster, and Voyager 1 successfully reached its destination. Now, both unmanned Voyager spacecraft were en route to Jupiter. Voyager 1 was expected to reach the planet in March 1979, followed by Voyager 2 4 months later. The journey would then continue to Saturn. At the time of the closest encounter on November 12, 1980, Voyager 1 would have traveled 1.4 billion miles through space. The story unfolded with critical decisions and discoveries shaping the course of these historic space missions. The Voyager spacecraft was equipped with an optical guidance system that enabled them to independently determine their attitude in space. Precise orientation was crucial for various tasks, and the system included a sun sensor mounted in the high-gain antenna, allowing the probe to align itself with the Sun and Earth in the inner solar system. The spacecraft's body then rolled until two star trackers, working in a binocular fashion, locked onto a known star, typically Canopus, one of the brightest stars in the celestial sphere. These celestial navigation instruments provided data to the guidance computer on board Voyager. The guidance computer, named High-Pace Programmable Attitude Control Electronics, featured two redundant plated wire memory banks, each with fixed and reprogrammable memory. High-Pace monitored and controlled various elements, including sun sensors, star trackers, the movable scanned platform on the science boom, and a small inertial guidance unit. If Voyager needed to break its optical sun-celestial attitude lock, a 3-axis gyro could measure the drift away from the optic lock point, allowing it to memorize its direction for short periods. This capability was useful during scientific observation or instrument calibration. There were 3 computer systems on board the spacecraft. The second one, the Flight Data System, controlled the science instruments and formatted all data for transmission to Earth. Given Voyager's distance during planetary encounters, instructions on where to point cameras, when to take readings, and when to transmit were loaded onto its computers via ground transmission. The Voyager ground team played a critical role in ensuring precise execution, as small errors in the sequence could result in missed opportunities. The computer command subsystem acted as the conductor of this orchestra, controlling both the flight data system and the guidance computer. It issued master commands for spacecraft sequences, whether it was an attitude maneuver or a series of timed commands for the science instruments. Command signals from the ground were transmitted through the Deep Space Network system of massive radio telescopes at a rate of 16 bits per second to the spacecraft. While there was a minor concern about the science boom aboard Voyager 2 not being latched due to a missing confirmation signal, there was no indication that the boom was loose or in motion at this point. Voyager 1 and 2's dance with Mars and each other. Just 22 days after launch, on September 16, 1977, Voyager 1 was positioned 21 million kilometers from Earth. At this point, it calibrated its camera system by capturing an image of Earth and the Moon in a single frame. This marked the last time Voyager 1 captured Earth as anything more than a pale blue dot. Throughout the end of 1977, both Voyager spacecraft performed several small mid-course pulses with their hydrazine thrusters, known as trajectory correction maneuvers. These maneuvers nullified small errors and ensured optimal placement before the critical Jupiter encounter. During the outbound coast, minor issues common to spaceflights arose and were resolved, including a slight propellant deficit, a failure in one of the CCS computers, sticky motors, and the decision to lock onto the star deneb instead of canopus to minimize solar radiation pressure by rolling Voyager 2 180 degrees. The spacecraft passed the orbit of Mars in mid-November 1978, and on December 15th, Voyager 1 overtook Voyager 2, now worthy of its number. Both continued unhurried observations of the celestial sphere and the Sun for instrument calibration purposes, although some scientific data was obtained during this phase. Small systems failures persisted but were consistently addressed, including a frozen scan platform, a stuck filter wheel on the photopolarimeter, and a decrease in sensitivity in the plasma experiment. A major issue arose in Voyager 2 when the primary radio receiver experienced an unknown failure, causing excessive current and blowing its fuses. For an entire week, all contact with Voyager 2 was lost, but communication was eventually re-established. The primary receiver was determined to be permanently damaged, and the secondary receiver, due to a faulty capacitor, could not correct for Doppler shifts, necessitating alternate methods of positional navigation. JPL's mission bulletins from 1978 described Voyager 2 as beleaguered, and the mission faced significant challenges. Despite the setbacks, Voyager 2's computer was loaded with commands to provide a minimal science encounter at both Jupiter and Saturn in case the radio uplink was lost permanently. Despite consuming about 10% of their hydrazine maneuvering propellant during the cruise phase, both Voyager spacecraft continued their mission. Drifting and chaos were inevitable due to the motion of the scan platform on the science boom, but the hydrazine thrusters were used to counteract this and maintain a stable orientation. The narrow-angle television camera experienced pointing errors, requiring significant post-processing and stabilization on the ground to create coherent sequences. The wide-angle camera, though slightly better, still presented challenges with a field of view spanning 3 degrees. The Voyager mission faced risks, but engineers worked diligently to navigate and overcome the complexities of deep space exploration. Voyager 1 gracefully entered Jupiter's expansive space, presenting a visual narrative that defied the constraints of time. Through its lens, the probe penetrated Jupiter's outer layer, revealing aspects hidden from plain view. But how did the initially black and white images transform into the vibrant colors we now recognize? Well, let's find out. Crafting Jupiter's true colors with Voyager's filtered vision. On January 4th, 1979, Voyager 1 entered its observatory phase as it approached Jupiter, leading to a surge in scientific activities. The spacecraft performed daily scans using its scientific instruments. The highlight occurred on January 30th, when Voyager 1 conducted an intensive 4-day imaging session of Jupiter, capturing real-time pictures every 96 seconds for an impressive 100 hours, equivalent to 10 rotations of the gas giant. When these raw images, without any alterations, were played back quickly, they unveiled the captivating movements of Jupiter's atmospheric features. Yet, a question arose. How did these black and white images transform into the vibrant, colorful representations we commonly associate with celestial bodies? The answer lies in filter wheels, similar to those found in the photopolarimeter. The television cameras featured a rotating wheel of translucent filters, including green, blue, orange, ultraviolet, and clear. Some filters had a scientific purpose by isolating specific wavelengths, while others contributed to creating color. By capturing 3 monochrome images through green, orange, and violet filters, and later applying their respective colors in a dark room on Earth, the final synthesized color image emerged, a representation of Jupiter's true color distribution. Every color image from Voyager essentially combined at least 3 separate monochrome exposures, offering insight into the world of our solar system's largest planet. Voyager's unique approach to image capture, along with the vast distances it covered and inherent system errors, required post-processing by humans back on Earth. This collaborative effort, which began in 1979, continues to this day, with enthusiasts and experts applying digital processing and enhancement techniques to uncover the secrets embedded in decades-old raster scans. By late February 1979, Voyager 1 had delved into Jupiter's realm, providing a front-row seat to the planet's largest single feature, the magnetic field. This magnetic field, nearly 7 million kilometers in the Sun's direction and 20,000 times stronger than Earth's, resulted from electrical currents in Jupiter's outer core, primarily composed of liquid metallic hydrogen. Unexpectedly, Voyager 1 encountered a substantial ring of plasma around Jupiter, a torus made up of sulfur and oxygen ions. This plasma torus, rotating with the planet, reshaped the magnetic field into a flattened disk. Electrons within the plasma produced a distinctive radio signature, depicting Jupiter as a pulsar. The gas giant, mainly composed of hydrogen and helium, displayed a varied tapestry of tans, browns, and oranges. Jet streams, alternating zones, and bands characterized its outer atmosphere, concealing a mysterious, solid, rocky core beneath. As Voyager 1 captured the intriguing features of Jupiter, including the iconic Great Red Spot, a centuries-old anticyclonic storm larger than Earth, it revealed new insights into the majestic and dynamic realms of our solar system's largest planet. The first documented sighting of the Great Red Spot through Earth-based telescopes dates back to 1831, credited to German astronomer Heinrich Schwab. Nevertheless, periodic observations of the spot occurred throughout the 19th century, and claims suggest it might have been seen as early as 1665 by Englishman Robert Hooke. The uncertainty arises from Hooke's mention of a spot in one of the belts of Jupiter in Volume 1 of the Philosophical Transactions of the Royal Society, which could have referred to one of Jupiter's 4 large innermost moons discovered by Galileo in 1610. While the exact date of the Great Red Spot's discovery remains contentious, it is undeniable that over time, it has been diminishing. Currently, it is only half as large as it was in the 19th century, prompting questions about its future, whether it will disappear during our lifetimes or undergo a resurgence and grow again. Jupiter's immense size, being 2.5 times that of all other planets in our solar system combined, exerts a substantial gravitational influence. Its mass is so significant that it induces a wobble in our Sun, with the center of gravity lying outside the Sun's surface. In essence, Jupiter and the Sun orbit each other, although it's a close call. As Jupiter radiates heat and energy over time, it cools and contracts. Believed to be the oldest planet in the solar system, Jupiter, during its formation, was much hotter and nearly twice its current size. Jupiter could have potentially become a star if it had approximately 75 times more mass, meeting the conditions for hydrogen fusion. Interestingly, most stars in our galaxy exist in binary systems, where 2 or more individual stars orbit each other. Single stars like our Sun are the exception rather than the rule. Jupiter could have been a companion star, but it fell short of accumulating enough mass for that role. Voyager 1's dive into Jupiter's volcanic moon. As Voyager 1 continued its journey past Jupiter, it turned its focus to the planet's moons. In 1979, Jupiter had 14 known moons, but subsequent missions like Galileo have increased the count to over 80. 4 of these moons, discovered by Galileo in 1610, are named the Galilean moons and are particularly noteworthy due to their size and uniqueness. One intriguing phenomenon around Jupiter is the torus of plasma that significantly distorts its magnetic field. This cold, dense plasma, originating from Jupiter's innermost Galilean moon, Io, moves outward, carried by Jupiter's magnetic field and eventually dispersed by the solar wind. Io, first observed by Galileo in 1610, appeared as a fifth magnitude point of light. Only in the mid-20th century did observations suggest Io's unusual nature, with a surface dominated by evaporates of sodium salts and sulfur dioxide. Due to intense tidal forces from Jupiter, Io experiences constant volcanic activity, boasting around 400 active volcanoes. The ejected material forms the plasma torus around Jupiter. During its encounter with Io, Voyager 1 faced extreme conditions, including 1,000 times the lethal dose of radiation for humans. Io's volcanic activity, intense radiation, and powerful electric fields make it inhospitable for life. Voyager 1 also observed Europa, Jupiter's second Galilean moon. With a diameter slightly smaller than Earth's moon, Europa displayed a chaotic pattern of icy linear on its surface. Composed mostly of water ice, Europa's reddish-brown regions are dirtied with clay-like materials and salts. Despite its surface temperature dropping to -138 degrees Celsius, the ice on Europa is as hard as granite. Europa's smooth surface, lacking mountains and craters, suggests the possibility of a subsurface ocean. Tidally locked to Jupiter, Europa experiences significant stress on its crust due to tidal forces, hinting at the possibility of plumes of water vapor and cryovolcanism. While conclusive evidence of a subsurface ocean is lacking, the idea of a warm, saltwater ocean beneath Europa's icy crust fuels speculation about potential life. Jupiter's tidal forces, not solar energy, play a key role in maintaining Europa's warmth. The cracks on Europa's surface, caused by tidal flexing, indicate a subsurface ocean driving the motion of the outer crust. Despite the challenges of drilling through kilometers of solid ice, scientists believe in the existence of a liquid water ocean beneath Europa's surface. Europa's potential habitability challenges the traditional concept of the habitable zone around a star. The energy for maintaining liquid water on Europa comes from Jupiter's tidal forces. While direct evidence of life remains elusive, Europa remains a priority in the search for extraterrestrial life within our solar system. The possibility of a liquid water ocean beneath its icy surface adds an intriguing dimension to the exploration of celestial bodies beyond Earth. Ganymede, Jupiter's third Galilean moon, orbits at a distance just over 1 million kilometers. Like Io and Europa, Ganymede is tidally locked, and its low eccentricity means that tidal heating is negligible. Despite being the largest and most massive moon in the solar system, even surpassing the planet Mercury, Ganymede's low density, less than half of Mercury's mass, suggests a composition of roughly equal parts rocky material and ice. In the 1990s, the Galileo mission conducted magnetic measurements of Ganymede, revealing a significant and persistent magnetic field around the moon. This surprising finding challenges expectations for an object of Ganymede's low density. Ganymede's magnetic field constantly shifts, leading to a theory proposing the presence of a massive subsurface ocean, similar to Europa. The fluid motion of saline water beneath the surface acts as a conductor, contributing to Ganymede's active magnetic presence. However, like Europa, there is currently no direct evidence of a subsurface ocean on Ganymede. If the model of a saltwater ocean is accurate, Ganymede's ocean would have to be exceptionally large, with estimates ranging from 100 to 800 kilometers in thickness. This would make it the largest ocean in the solar system, surpassing all the water on Earth. Despite these intriguing possibilities, if Ganymede does indeed possess an ocean, it is trapped beneath a crust of rock and ice, located 95 kilometers below the surface. Scientists remain uncertain about how Ganymede acquired its grooved terrain, similar to Europa's. Tidal heating is considered improbable given Ganymede's distance from Jupiter, leading to speculations about its formation closer to Jupiter before migrating outward. Ganymede's surface, covered in impact craters, is notably older than Europa's. Saturn's turbulent atmosphere and mysterious rings. Before the Voyager missions, it was thought that Ganymede and Callisto, the fourth Galilean moon, shared many characteristics. Both moons surpass the size of the planet Mercury, have relatively dark surfaces, and are lightweight. However, Voyager 1 uncovered distinctions, highlighting Callisto as having possibly the oldest surface among all moons or planets in the solar system, featuring numerous impact craters preserved over 4 billion years. Ganymede's surface, though ancient, is only a quarter as old as Callisto's. No signs of endogenic processes, such as volcanism or tectonic activity, have been identified on Callisto. Its low density suggests an ice-rich composition, with some models proposing the potential for a subsurface ocean based on magnetic data. However, the absence of supporting evidence raises questions about this interpretation. Callisto doesn't undergo tidal heating, and if there is a thick layer of ice, it's likely frozen solid. Callisto's minimal exposure to Jovian radiation on its surface makes it an intriguing target for potential human outposts. The presence of water ice on its surface holds promise for vital resources like drinking water, oxygen, and rocket fuel. As Voyager 1 crossed Jupiter's equator, a strategic maneuver exposed its television cameras for an unprecedented 11 minutes and 12 seconds, capturing an image that provided the first visible evidence of rings around Jupiter. These rings, faint and made up of thin dark dust, are believed to form from meteoroid impacts with Jupiter's moons, creating streams of fine particles into orbit. While Jupiter's rings are faint and delicate, the Voyager spacecraft delivered essential insights into the Jovian system, paving the way for future missions to explore the mysteries of this gas giant and its diverse moons. Despite initial challenges in the coast phase, the Voyager mission at Jupiter proved highly successful. Its impact was substantial enough to influence the ongoing Pioneer 11 mission, a half-ton probe en route to Saturn after encountering Jupiter in 1974. The Voyager probes had just completed their exploration of Jupiter and were en route to Saturn when Pioneer 11's schedule aligned for its closest approach in September 1979. Both Pioneer 10 and Pioneer 11 had played a role in the initial cancellation of the Grand Tour mission. However, with Voyager's triumph at Jupiter, NASA's Jet Propulsion Laboratory proposed redirecting Pioneer 11 to traverse Saturn's outer A-ring. This trajectory was crucial for Voyager 2's subsequent journey to Uranus. JPL argued for Pioneer 11 to act as a test subject, sacrificing some scientific objectives to pave the way for Voyager 2. Despite objections from the Pioneer team, NASA management sided with JPL, announcing Pioneer 11's role as a precursor, navigating through Saturn's outer rings. On September 1, 1979, as Pioneer 11 passed Saturn, it made significant discoveries, narrowly avoiding a collision with a previously undetected moon by just 2,100 nautical miles. The mission charted Saturn's magnetic field and encountered another previously unknown moon. Pioneer 11, serving as a test case, successfully traversed Saturn's outer rings, providing crucial insights into the viability of this trajectory for future missions. The Voyager team hoped for an extended mission, and Pioneer 11's successful passage through Saturn's rings added to their optimism. The rings, nearly 300,000 kilometers across and incredibly thin, were estimated to be no more than 100 meters or as thin as 20 meters. Pioneer 11 took just 4/5 of 1 second to traverse through the rings, demonstrating the challenges and potential hazards of this route. Despite its basic design in comparison to Voyager, Pioneer 11 played a crucial role as the first human-made object to reach and study Saturn. The faster-traveling Voyager probes were on course to encounter Saturn, each facing its own set of challenges, technical hitches, and scientific discoveries. Voyager 1 was scheduled to reach Saturn in November 1980, followed by Voyager 2 in 1981. The observations made during these encounters were expected to enhance our understanding of Saturn's unique features and intricate ring system. Saturn, with its seemingly calm pale tones, conceals a turbulent atmosphere where wind speeds can reach an astonishing 500 meters per second, equivalent to over 1,000 miles an hour. This turns Saturn into a planetary blender, where vigorous mixing erases much of its distinct features, leaving only faint bands visible. Undoubtedly, the most iconic feature of Saturn is its rings, initially observed by Galileo and correctly identified as rings by Dutch astronomer Christian Huygens in the 1650s. In the 1670s, Italian-born French astronomer Jean-Dominique Cassini detailed the structure of the rings and identified the largest gap, now known as the Cassini division. Saturn's rings showcase remarkable complexity, primarily composed of water ice, carbon, and organic compounds. Beyond the well-known rings, such as the G and E rings visible in upsun photographs, there's a more elusive one called the Phoebe ring. Positioned approximately 12 million kilometers from Saturn, this extensive and nearly invisible ring is significantly tilted and orbits retrograde, moving in the opposite direction to Saturn's spin and that of its other moons. A closer look at the diverse worlds orbiting the ringed giant. The origin of Saturn's rings has been a matter of discussion. Initial theories suggested that they were remnants from the planet's original planetary nebula. However, recent data from missions such as Cassini propose that the rings might be relatively young, potentially formed from impacts between Saturn's moons. Saturn has a distinctive feature called spokes in its rings, believed to be deformations caused by interactions between Saturn's magnetosphere and fine magnetic dust particles within the rings. These spokes display unusual behavior influenced by Saturn's powerful forces. In contrast to Jupiter, Saturn lacks a reddish hue and appears predominantly monochromatic with pale yellow tones. This color is believed to originate from crystallized ammonia clouds in its upper atmosphere. Below this upper atmosphere, Saturn is thought to have a series of dark belts and light zones, with its composition mainly consisting of hydrogen, including a significant amount of liquid hydrogen beneath the surface. Saturn's core is both hot and rocky, emitting more energy into space than it receives from the Sun. Due to its substantial size and rapid spin, Saturn is the most flattened planet in the solar system, with its polar and equatorial radii differing by nearly 10%. Alongside Jupiter, Saturn accounts for 92% of the planetary mass in our solar system. While storms do occur on Saturn, they are brief and challenging to observe. When storms do manifest, they appear as milky white fluid turbulence across the otherwise featureless banded face of the planet. Saturn boasts distinctive features that go beyond its iconic rings, including a hurricane-like vortex at its south pole and a unique hexagonal cap at its north pole. The sizable hurricane-like vortex, persisting for billions of years, is comparable in size to Earth. Meanwhile, the hexagonal cap, exhibiting intriguing fluid dynamics, challenges our comprehension of atmospheric phenomena. Laboratory recreations on Earth using water flow gradients mirror this hexagonal shape, shedding light on the impact of varying wind speeds across Saturn's latitudes. An additional peculiarity lies in Saturn's magnetic field, deviating from the patterns seen on Jupiter and Earth. In contrast to the typical 10-degree offset, Saturn's magnetic field is almost perfectly aligned with its rotational axis, possibly to a mere half a degree. This alignment contributes to Saturn's relatively weak magnetosphere, despite the field's impressive size, being 600 times that of Earth's. Saturn is orbited by a diverse collection of moons, with data from missions like Cassini significantly expanding our understanding of these celestial bodies. Noteworthy examples include shepherd moons such as Pan, Pandora, Prometheus, Janus, and Epimetheus, playing pivotal roles in maintaining the structure of Saturn's rings. Mimas, linked to the Cassini division, boasts a massive impact crater resembling the Death Star. Venturing farther out, Enceladus, an icy moon within the E-ring, stands out as a substantial discovery. Cassini, years after the Voyager flybys, unveiled geysers at Enceladus's south pole, expelling warm, salty water, silica-rich sand, nitrogen, and organic molecules into space. Despite its modest diameter of just over 500 kilometers, Enceladus defies expectations by retaining heat energy, possibly sourced from an unidentified mechanism. The subsurface ocean, warmth, and organic-rich plumes on Enceladus position it as a prime contender for potential extraterrestrial life, surpassing even Mars and Europa in this aspect. Beyond Enceladus, Tethys, an icy moon, displays various-sized impact craters. Dione follows, revealing rugged terrain marked by scars and canyons, especially on its trailing hemisphere. As we move outward, the moons increase in size. Rhea, the larger counterpart of Dione, presents itself as an icy, desolate world with evidence of ancient impacts and interactions with rings and debris. However, a significant shift occurs about 750,000 miles away, where Saturn's largest moon, Titan, stands out. Titan is not only unique in the Saturn system, but also in the entire solar system. For centuries, it remained a mysterious, featureless orange ball. It possesses a genuine atmosphere, so thick that despite having a surface gravity slightly less than our moon's, the atmospheric pressure on Titan is 1.5 times greater than sea level on Earth. Titan's atmosphere, composed of over 95% nitrogen gas, includes haze and humidity from methane gas, resulting in a complex climate akin to Earth's water cycle. Titan's lakes, filled with liquid methane and resembling Earth's Great Lakes, are situated below a hazy orange atmosphere at an altitude more than twice that of Earth's recognized boundary of space. These lakes may contain large amounts of liquid hydrocarbons, formed without the involvement of living organisms through ultraviolet radiation from the sun. Titan undergoes minimal evaporation, resulting in extended periods of dryness, followed by intense hydrocarbon rains and widespread flash floods. Despite challenges, such as a design flaw in the Huygens probe's descent, observations from Cassini and Huygens have unveiled Titan's extremely cold and humid conditions. The moon exhibits stable bodies of liquid, along with a climate that includes lakes, clouds, and rain. Titan's surface, near the methane triple point, allows for changes in state based on subtle fluctuations in energy and pressure. The culmination of the mission, marked by observations of Titan, represented a crucial moment, redirecting Voyager 1 from other planets toward the exploration of this mysterious moon. In January 1981, Voyager 1 shifted focus from planetary exploration to unraveling the mysteries of our sun's magnetic field and its cosmic interactions. As it ventured into interstellar space in 2012, it posed profound questions about the solar system's limits. But what valuable insights did Voyager 1's entry into interstellar space provide about the dynamics between our sun and the vast galactic expanse? From Saturn's rings to Uranus's cosmic tilt. In January 1981, Voyager 1 completed its planetary exploration and shifted its focus to studying the sun as it exited the solar system. Continuing its interplanetary mission, the spacecraft collected data on the sun's magnetic field and its interaction with the galaxy. The ongoing Voyager interstellar mission analyzes magnetic field lines, plasma oscillations, and interstellar medium density to understand these interactions. Voyager 1 officially entered interstellar space in 2012, providing valuable data that has expanded our understanding of the solar system's boundaries. On August 25, 1981, Voyager 2 faced a critical issue near Saturn, within its shadow and out of communication with Earth. The scan platform became horizontally stuck, a problem discovered when communication was re-established. Recognizing the issue's severity, the ground team promptly commanded the platform to elevate its instruments away from the sun, preventing potential damage. This setback led to the loss of planned observations, prompting troubleshooting efforts during the outbound trip. By August 28th, the platform's azimuth actuators began moving again, albeit with hesitant and slow responses. Scientific activities were temporarily halted for several weeks as the ground team conducted tests, indicating a likely mechanical problem within the spacecraft. Undeterred, the Voyager team publicly announced on September 23, 1981, their plan for a small mid-course correction burn to redirect the spacecraft towards Neptune during the Uranus flyby. To support Voyager 2's extended mission, significant changes were made due to diminished signal strength at Uranus. Antennas were grouped together, utilizing multiple large radio dishes simultaneously, and several antennas were physically enlarged. This unintentionally advanced the capabilities of the Deep Space Network for planetary radar astronomy. The Voyager 2 scan platform issue was traced to lubrication and worn gear mechanisms, but its movement was conserved, and the prospects for a successful Uranus encounter were positive. Voyager 2's billion-mile journey from Earth provided unprecedented images of Saturn, offering a close-up view of the ringed planet. The spacecraft's trajectory was precisely controlled through radio tracking, photograph analysis, and precise maneuvers with small hydrazine rocket engines. The initial trajectory's precision allowed the spacecraft to conserve fuel, ensuring ample reserves for its journey out of the solar system after the Saturn encounter. Uranus, discovered in 1781 by Sir William Herschel, had a controversial naming history. Initially, Herschel wanted to name it after King George III, leading to the term Georgian star. However, the name Uranus, proposed by German astronomer Johann Bode, gained acceptance. Uranus, along with Saturn, is the only planet whose rings are observable from Earth with advanced technology. Uranus's rings were discovered in 1977, the same year Voyager 2 was launched, using a flying observatory operated by NASA. This discovery was facilitated by observing Uranus passing between Earth and a distant star, causing unexpected infrared fluctuations. In the intricate dance of our solar system, Uranus emerges as a unique celestial entity, showcasing a fascinating story of planetary quirks. Unlike its planetary peers, which elegantly follow a common cosmic axis, Uranus takes a bold deviation. It literally tilts on its side. Envision a cosmic ballet where everyone adheres to the same routine, but Uranus opts for independence, twirling with its rings and moons tilted a significant 98 degrees from the typical celestial plane. The mystery of Uranus's peculiar tilt directs us to a shocking past, a period when the foundational components of our solar system engaged in a celestial contest akin to bumper cars. Picture a disorderly clash of cosmic entities, competing for space, colliding and assimilating one another. Uranus, it seems, underwent a transformative impact, compelling it to assume a sideways orientation. Even its moons, obediently orbiting along its shifted equator, bear witness to this celestial ballet. As our outer planets participated in a compelling gravitational struggle, Uranus found itself positioned at the solar system's outer limits. Initially holding the distinction of being the farthest planet, it yielded its status to Neptune, its sibling, in the course of a cosmic migration. This era of orbital upheaval is not only recorded in computer models, but also etched on the lunar surface, where intense meteoroid bombardment unveils the remnants of a distant cosmic conflict. Is it conceivable that additional planets, now cosmic nomads, were expelled rather than eliminated during this celestial conflict? This notion sparks the imagination, suggesting that these wandering entities might still traverse the Milky Way, remnants of a bygone era when they orbited our sun. Fast forward to the present, and Uranus orbits at an average distance of 19 astronomical units, following an eccentric path that fluctuates between 18 and 20 astronomical units in its cosmic journey. As a distant traveler, it completes its orbit around the Sun in a leisurely 84 years, while its distinctive axis undergoes a full rotation every 17 hours and 14 minutes. Picture the poles, each experiencing an astonishing 42 years of continuous sunlight, succeeded by an equally prolonged period of desolate darkness. The puzzling secrets of Uranus and Voyager's glimpse. In 1986, Voyager 2 discovered what initially appeared to be an ordinary pale blue sphere. However, recent advances in imaging technology have unveiled a dynamic and intricate world on Uranus. Despite its past reputation as a dormant planet, Uranus showcases detailed cloud formations and subtle brightness variations across its latitudes. The key to understanding Uranus's mystery lies in its cold nature. It emits minimal thermal energy, with internal heat levels much lower than its gas giant counterparts. The frigid temperatures within Uranus's atmosphere, dropping to a remarkable 49 Kelvin or -371.5 degrees Fahrenheit, suggest a historical event may have stripped the planet of its original heat, resulting in a perpetual cosmic cold spell. As we contemplate these mysteries, Uranus continues its slow celestial dance, remaining an icy mystery in our cosmic exploration. Uranus shields a mysterious puzzle concealed by a barrier that appears to safeguard its internal warmth. Like its gas giant counterparts, Jupiter and Saturn, most of Uranus's volume is believed to consist of a dense layer of compressed gaseous and liquid hydrogen. However, beneath this familiar exterior, Uranus stands apart, featuring a composition of solid water, methane, and ammonia ice, creating a mantle that surrounds a small rocky core. A surprising element in Uranus's narrative is the presence of a mere 3% methane concentration in its upper atmosphere, contributing to its distinct bluish color. The space surrounding Uranus presents an unexpected twist, with its thermosphere hosting hot gas particles, reaching a scorching 850 Kelvin. The origin of this intense heat remains a cosmic puzzle, as known variables such as solar radiation and magnetic field activity fall short of explaining this phenomenon. Uranus boasts one of the most unusual magnetic fields in our celestial collection. Tilted almost 60 degrees away from its rotational axis, this magnetic field doesn't originate from the planet's center and showcases a remarkable tenfold strength difference between its northern and southern hemispheres. This anomaly suggests unfamiliar mechanisms, possibly driven by the convection of conductive material closer to the surface or a redirection of a typical magnetic field through a process known as magnetic shielding. Venturing into speculation, the idea of a concentration of diamond-like material in Uranus's southern hemisphere arises. This compressed carbon, similar to diamond, could potentially possess magnetic shielding properties, giving rise to a celestial spectacle of colossal diamond icebergs ascending through the depths of Uranus. However, these imaginative scenarios remain speculative, as the precise nature of Uranus's magnetic field continues to elude our comprehension. Our only emissary to Uranus, Voyager 2, lacks the advanced tools necessary to unravel the secrets of the ice giant's interior. Approaching Uranus almost perpendicular to its rotational axis, the observation window is limited to a brief 5.5 hours, a significant departure from the more leisurely observations conducted on previous planets. This fleeting encounter poses a challenge, compelling Voyager 2 to rapidly gather data from all of Uranus's moons simultaneously, leaving little room for the luxury of switching between them. At 10 a.m. on January 24, 1986, Voyager 2 commenced an extraordinary journey toward Uranus, marking the beginning of an unparalleled cosmic exploration. However, just 4 days later, on January 28th, an unforeseen incident diverted global attention from this celestial undertaking. Amidst the eager anticipation and countdown, tragedy befell on that fateful day. The Challenger, undertaking its 10th mission, STS-51L, experienced a catastrophic event during liftoff. A minute before the planned launch, as the Challenger's main engines ignited, an explosion erupted from one of the solid rocket boosters. In a heart-wrenching scene, the entire spacecraft disappeared into a fireball, disintegrating into spiraling debris. The 7-member crew of the Shuttle Challenger lost their lives in the tragedy, casting a somber shadow over the nation. While Voyager 2's encounter with Uranus coincided with this tragic event, any excitement for the cosmic achievement came to an abrupt halt. The nation mourned the loss of the astronauts, leading to an almost 3-year hiatus for the shuttle program, which was then in its 5th year. Uranus, positioned at a considerable distance from the Sun and enveloped in darkness 400 times dimmer than Earth's, posed a unique challenge for Voyager's cameras. To capture meaningful images, the shutters had to remain open for extended periods. However, the scan platform's movements occurred in dimensional steps, elevation followed by azimuth, and so on, preventing a precise, prolonged pointing lock on celestial objects and potentially resulting in blurred images. Operational adjustments were essential for the Uranus encounter. The Voyager team strategically utilized the gyroscopes within the spacecraft's guidance system, enhancing the scan platform and target tracking. Despite being fuel-intensive, this method was considered worthwhile, representing humanity's singular opportunity to closely observe the mysterious 7th planet and its moons. Voyager's farewell to Uranus and the quest ahead. In the vast expanse of space, radio signals and commands encountered a delay of 2.5 hours to travel between Earth and Voyager. Undaunted by this challenge, Voyager 2 diligently captured a series of long-exposure images of Uranus, providing a direct view of its rings due to the planet's unique tilt. The Voyager team, motivated by the desire to uncover the secrets of Uranus, took a calculated risk to ensure that this brief encounter would significantly contribute to our understanding of the outer regions of our solar system. During its journey through the cosmos, the spacecraft meticulously captures images and conducts in-depth studies of the 5 well-known moons orbiting Uranus: Miranda, Ariel, Umbriel, Titania, and Oberon. These moons, named after characters from the literary works of William Shakespeare and Alexander Pope, reflect the English origin of their discovery. Uranus's lunar companions, known for their small size and profound darkness, present a fascinating celestial display. The largest among them, Titania, is only half the size of our moon, with a diameter of less than 800 kilometers. Despite the identification of at least 27 natural satellites around Uranus, these 5 moons stand out as the most significant. A widely accepted theory proposes that these moons originated following a massive impact that disrupted Uranus, potentially accounting for their remarkable similarities. Among these moons, Miranda, the smallest and closest to Uranus, stands out due to its unique combination of small size and chaotic surface features. A closer examination reveals a terrain that has undergone significant changes, displaying the most extensive cliffs and deepest canyons in our solar system. Miranda's surface, adorned with ancient impact craters, raises questions about its history. Could tidal heating during a more elliptical orbit or active cryovolcanism be responsible for these distinctive features? These unanswered questions, spurred by Voyager 2's thorough observation, highlight the importance of a dedicated exploration mission to unravel Miranda's mysteries. As we explore the complexities of celestial bodies, it's essential to acknowledge the collective effort behind such undertakings. The Spaceflight Operations Facility, though just a part of the broader team, plays a crucial role in ensuring Voyager 2 accomplishes its mission. Beyond the spotlight, numerous individuals contribute to the success of space projects, emphasizing teamwork in advancing our exploration of the solar system. Voyager 2 was to bid farewell to Uranus and set its course for Neptune, marking the conclusion of the initial exploration phase in our planetary exploration program. While mariners, Vikings, and Voyagers have provided valuable knowledge, there is still much to uncover. The individuals guiding these spacecraft and the scientists interpreting the data they collect serve as esteemed teachers on our cosmic journey. Recently, the Planetary Science and Astrobiology Decadal Survey, conducted every 10 years, has presented its recommendations to both NASA and Congress. The proposal suggests an ambitious project: the creation of an advanced spacecraft designed to orbit Uranus and study its moons extensively. This mission aims to go beyond a quick flyby, similar to Voyager 2, by deploying a sophisticated probe, like Cassini, equipped to perform detailed and precise measurements over an extended period. Uranus currently holds a special place in planetary science, designated as a high-priority exploration target. The idea of witnessing a dedicated mission to this mysterious planet within our lifetimes is intriguing, but it's important to note that the journey has just begun, and any significant discoveries are likely years away. The precise calculation of Uranus's orbital path dates back to 1783, thanks to Pierre-Simon Marquis de Laplace. Subsequent years revealed puzzling irregularities in Uranus's orbit, leading to speculation about external gravitational influences. In 1841, English astronomer John Couch Adams and French astronomer Urbain Le Verrier independently set out to determine the position of this elusive celestial body. By 1846, Le Verrier, confident in his findings, published his predictions. Adams had already generated 6 potential solutions, but Le Verrier, with remarkable precision, narrowed it down to 1. Despite facing criticism at the Paris Observatory, Le Verrier's persistence paid off when Johann Galle, director of the Berlin Observatory, spotted Neptune within 1 degree of the predicted position. Neptune, initially mistaken for a star due to its faintness and distance, remained unknown to ancient cultures. The successful prediction and subsequent discovery of Neptune not only validated Isaac Newton's gravitational laws over vast distances, but also highlighted the collaboration between French calculations and German observations. Navigating challenges beyond Uranus. As Voyager 2 moves away from the Sun, it encounters increasing challenges. The diminishing sunlight becomes a significant obstacle, affecting the spacecraft's ability to navigate and maintain its orientation in space, known as attitude lock. To address this issue, Voyager 2 relies more on its cameras, using extended exposures to gather detailed attitude information. Between Saturn and Uranus, the spacecraft captures an impressive set of nearly 100 photos as part of its optical navigation strategy. This strategy involves taking multiple shots of the space between these distant planets. The intensity of this process increases as Voyager 2 approaches Uranus, resulting in an even greater number of photos taken in the vast expanse between Uranus and Neptune, surpassing the previous count. Approaching Neptune, Voyager 2 engages in a careful photographic process. Several long shots are directed towards Neptune, and the images undergo thorough analysis. Any imperfections and residual marks are meticulously removed, considering the natural rotation of the probe. Points of light are documented, and any differences between image frames are examined. Points that have moved more than expected due to the probe's rotation are identified as newly discovered moons, showcasing the unexpected findings Voyager 2 continues to make. In the vastness of space, where light is limited, Voyager 2's camera shutters remain open for extended periods, capturing details that would otherwise be difficult to observe. The challenge grows for the Voyager ground team, prompting them to develop innovative strategies for managing the probe's rotation. The original design of Voyager did not anticipate a complete halt to angular momentum due to the complex nature of its moving components. Even seemingly minor actions, such as starting and stopping the tape recorder inside the probe, can collectively influence its trajectory over time. To tackle these challenges, the ground team implements software changes with the goal of minimizing motion in the scan platform, improving gyroscope turn rates, and making various other adjustments. These modifications are crucial to reduce the spacecraft's movement, enabling longer exposure times for capturing images without compromising the clarity of the collected data. Compensating for the probe's rotation becomes a central focus for the Voyager ground team. By the late 1980s, when Voyager 2 reaches Neptune, the light levels are only 40% of those at Uranus. The planet appears an astonishing 900 times dimmer than Earth, presenting a significant challenge for optical data gathering. The longer exposure times raise the risk of image smearing, posing a threat to the mission's primary objective of obtaining high-quality photographs. Maintaining the spacecraft's stability during its rapid journey through uncharted space becomes a top concern for the Voyager team. Voyager 2 successfully reached Neptune in August 1989, marking its concluding encounter with a planet. Recognizing that the probe's trajectory beyond Neptune had limited scientific significance, the ground team strategically executed a mid-course burn in 1987. This maneuver positioned the spacecraft over Neptune's North Pole, facilitating a close flyby of Triton, Neptune's largest moon. The Voyager team's precision and adaptability demonstrated their dedication to extracting valuable scientific data from the outer regions of our solar system. In contrast to its gas giant counterparts, such as Jupiter, Saturn, and Uranus, Neptune stands out due to its unique celestial companion, Triton. Triton, the solitary major moon of Neptune, remarkably holds 99.5% of all measured mass in orbit around the distant ice giant. This sets it apart from the 13 other recognized satellites, which are small, asteroid-like objects. Triton, smaller than Earth's moon, presents an otherworldly environment with temperatures dropping to a shocking 390 degrees below Fahrenheit. The frigid conditions have frozen nitrogen into an icy polar cap, visible as the striking white feature at the South Pole. Amidst the icy landscape, dark streaks emerge, revealing active geysers. Initiating the Voyager mission marked a significant advancement in humanity's pursuit of cosmic knowledge. This mission explored the mysteries surrounding Neptune and its fascinating moon, Triton, pushing the boundaries of our understanding of distant planets. What if the mysteries surrounding Neptune and Triton hold the key to unraveling the profound secrets of the universe? Voyager's legacy of discovery in the outer reaches. The Voyager mission, with its exploration of Neptune and Triton, reshaped our understanding of the solar system. The icy moon, with its dynamic geological features and unexpected characteristics, defied previous assumptions about planetary bodies. Voyager's discoveries not only altered our perception of planets, rings, magnetic fields, and moons, but also laid the foundation for future explorations of the outer planets. Neptune, distinct from Uranus, has a more typical tilt on its axis, resulting in noticeable seasonal changes. Despite its vast distance from the Sun, Neptune's orbit is remarkable, taking an impressive 164.8 Earth years to complete one orbit. No human has experienced a full Neptunian year, with the first completion occurring only in 2011, long after Neptune's discovery. Like Uranus, Neptune is classified as an ice giant. It lacks a solid surface, having a complex structure with multiple layers, different pressures, and various phases of matter. Determining the rotation of such a distant planet is challenging, but studying the shape of its magnetic field provides insights into its spin. Notably, Neptune's atmosphere shows different rotation rates across latitudes. Equatorial regions complete one full rotation every 18 hours, while the magnetic field completes a rotation every 16 hours. In contrast to its neighboring ice giant Uranus, Neptune emits a significant amount of heat and energy into space, driving a dynamic weather system in its atmosphere. Slightly more massive than Uranus, Neptune features visibly active cloud formations and storms. The outer layers consist mainly of hydrogen and helium, with a ratio of approximately 80 to 20%. Additionally, a small amount of methane in the upper atmosphere gives the planet a distinctive bluish hue, similar to Uranus. In the vastness of our solar system, Neptune remains a captivating mystery. The data collected by Voyager 2 stands as evidence of the enduring legacy of exploration and discovery. The complexities of Neptune's moons, its unique orbit, and the lively dynamics of its atmosphere continue to fascinate scientists, paving the way for future missions to unravel the mysteries of the outer planets. Neptune's upper atmosphere, distinguished by its slightly greater transparency compared to Uranus, provides a celestial view filled with intriguing details. Through further examination, scientists have found that Uranus displays cloud features and banding remarkably similar to those seen in visible light on Neptune. This interesting similarity is attributed to a higher concentration of methane in the upper atmosphere and a thinner icy haze layer on Neptune. These conditions, likely influenced by the higher ambient energy on Neptune, contribute to the planet's deeper, darker blue color and improve the visibility of atmospheric details. Voyager 2's meticulous observations reveal captivating phenomena in Neptune's atmosphere. The presence of white clouds is believed to indicate concentrations of methane ice particles. Among these features is the identification of circular storms, with the largest being named the Great Dark Spot. Similar to Jupiter's Great Red Spot, this massive storm is classified as an anticyclone, representing a region of high pressure and revealing darker layers beneath the haze. However, unlike its Jovian counterpart, the Great Dark Spot's lifespan seems to be much shorter. By 1994, when Hubble imaged Neptune again, the Great Dark Spot had completely vanished. Subsequent observations have identified new storms in different locations, indicating a pattern of emergence and dissipation. The exact mechanisms governing the formation and dissipation of these circular storms remain a subject of ongoing scientific investigation. Neptune's atmosphere is characterized by the fastest winds of any planet in our solar system, surpassing even the transonic belts of Saturn. Near the equator, prevailing westward jet streams move against Neptune's eastward rotation at astonishing speeds, clocking in at nearly 600 meters per second, or 1,300 miles per hour. This dynamic atmospheric behavior sets Neptune apart as a planetary giant with unique meteorological activity. Neptune's Kuiper connection. Despite being 50% farther from the Sun than Uranus and receiving only 40% of the relative solar energy, Neptune's internal energy powers the solar system's fastest and most dynamic planetary winds. Additionally, Neptune's gravitational influence extends beyond its immediate vicinity, significantly shaping and maintaining the Kuiper belt, a distant outer asteroid belt just beyond its orbit. Without Neptune's gravitational pull, the Kuiper belt might have merged into a remote icy planet. Among the celestial inhabitants of the Kuiper belt are several dwarf planets, including Orcus, Haumea, and Pluto. Neptune's unexpected arrival in their celestial neighborhood likely played a crucial role in their early development. It's important to note that Neptune did not initially form in its current distant orbit. Instead, it migrated relatively late during the solar system's formation. This intriguing migration adds another layer to the complex narrative of our solar system's evolution, with Neptune's influence reaching across vast distances and shaping the dynamics of the outer reaches of our celestial neighborhood. The Kuiper belt, a vast region beyond Neptune, spans nearly 20 times larger than the inner asteroid belt and hosts some of the solar system's most unusual and ancient celestial bodies. Within this expansive space reside mysterious objects that defy easy classification, contributing to the scientific fascination surrounding this distant region. In a surprising discovery, Voyager 2's examination of Neptune revealed a magnetic field orientation similar to its sibling planet, Uranus. This means that Neptune's magnetic field is tilted significantly in relation to its rotation axis, much like Uranus. Like Uranus, Neptune's magnetic field isn't uniformly strong around its center. Notably, Neptune's magnetic field is off-center by about half the planet's radius, which is even more pronounced than the already notable offset seen in Uranus. This challenges previous assumptions that Uranus's tilted magnetosphere was solely due to its unique sideways orientation. The shared phenomenon with Neptune implies the existence of an internal mechanism causing this unusual magnetic behavior on both planets. Voyager 2's exploration also includes Neptune's intriguing moon, Triton. Triton presents a celestial body that challenges conventional theories of moon formation. Not only does Triton orbit in the opposite direction to Neptune's rotation, but it also has an orbit significantly inclined away from the planet's rotation axis. This unique orbit has led scientists to suggest that Triton wasn't originally formed near Neptune, but was instead captured by the planet's gravitational influence. Mathematical models indicate that Triton is gradually moving inward and will eventually breach Neptune's Roche limit in the distant future. This could result in Triton disintegrating into a brilliant ring system before potentially colliding with Neptune's atmosphere. Triton's surface, as observed by Voyager 2, reveals a captivating and diverse terrain with circular depressions, rugged ridges, impact basins, craters, smooth plains, frosty deposits, and cantaloupe terrain. This unique landscape is not found on any other celestial body. Scientists theorize that cryovolcanism, a geological process involving the eruption and modification of landscapes through the release of volatile substances like water, methane, or ammonia, is responsible for such intricate topography. About 55% of Triton's surface, as directly imaged by Voyager 2, is covered in frozen nitrogen, showing interesting similarities to Pluto's surface composition. While Triton shares similarities with Pluto in terms of its frozen nitrogen cover, it seems to lack the dark reddish hydrocarbon sludge observed on Pluto's surface. However, our understanding of Triton is a work in progress, with a substantial portion of its surface, notably one whole side, remaining unobserved. Additionally, telescope observations in the 1960s suggested Triton reflected more red light than indicated by Voyager 2's observations in 1989. This apparent change in Triton's appearance over time may be attributed to cryovolcanism, suggesting that this captivating moon may look different today than captured in the 3 decades-old photographs from Voyager 2's historic flyby. As Voyager 2 captures images of Neptune with the sun behind it during its planetary encounters, it reveals new and previously unseen rings. These remarkable images result from an extraordinary 591 seconds of exposure, an almost unprecedented duration by earthly standards, nearly 10 straight minutes of uninterrupted light gathering. Carl Sagan's vision for extraterrestrial communication. In 1989, Voyager 2 completed its planetary phase and transitioned into the interstellar phase of its mission after departing from Neptune. Similar to its counterpart, Voyager 1, it began observing our Sun, meticulously mapping and measuring its magnetic field while venturing deeper into space. Each Voyager spacecraft carries a special artifact called the Golden Record, a gold-plated 12-inch two-sided stereo phonograph record. This record is housed in a case, accompanied by a small stylus designed to read and play back the audio information embedded in it. The idea of including a message for extraterrestrial intelligence can be traced back to the Pioneer 10 and 11 missions. The initiative to include a message for potential extraterrestrial contact on the Pioneer probes originated with Eric Burgess, an English journalist. He proposed this idea to Dr. Carl Sagan, a respected NASA advisor and director of Cornell University's Laboratory for Planetary Studies. Dr. Sagan, later known for his role as a prominent science communicator and advocate for the search for extraterrestrial life, convinced NASA to attach a small, lightweight plaque onto the Pioneer probes. This concept was further developed for the Voyager mission, with Dr. Sagan creating detailed instructions on the Voyager record covers. These instructions, if followed, would enable an alien intelligence to decipher and access the contents of the records. Notably, Carl Sagan, although not a member of the Voyager team, had a controversial influence over NASA's operational affairs. The Golden Records, despite not contributing to the mission's objectives, serve as a rational attempt to establish a communication system free from cultural or circumstantial influences. Realistically, locating and reading Voyager's Golden Records may never occur due to their celestial size, lack of major radiation emissions, and being significantly smaller than even a small asteroid. The challenge faced by Sagan and the Golden Record team involved communicating complex ideas without relying on cultural or biological references. Recognizing that an alien intelligence might lack an understanding of human concepts like seconds, minutes, or hours, the team focused on universal constants, numbers, and figures derived solely from the cosmos. A key symbol on the Golden Record's cover is positioned at the bottom right. 2 hydrogen atoms, each with 1 proton and 1 electron. The depiction shows 1 hydrogen atom with its electron facing outward and the other with the electron facing inward. In a neutral hydrogen atom at its lowest energy state, the proton and the lone electron spin in opposite directions, known as anti-parallel spin. However, introducing a small amount of energy, whether from a collision with another atom or radiation, can excite the electron, causing it to enter a slightly higher energy state, where its spin aligns with the protons. In this higher parallel energy state, the electron and proton spin in the same direction. Eventually, the energy must dissipate, and the electron spontaneously drops back down to the ground state, emitting a small amount of energy in the form of radiation, a radio wave randomly emitted from excited hydrogen atoms that are widespread in the universe. This radio wave, present virtually everywhere, is not associated with any particular planet, star, or phenomenon. The line separating the 2 hydrogen atoms on the record cover measures 23 centimeters, representing the wavelength of this radiation. This wavelength, measured in hertz, serves as the basic unit of time, and all other symbols on the record are represented in binary code within this temporal framework. The information embedded in the cover acts as a guide for using and comprehending the Golden Record. The first side of the stereo record is straightforward, containing music, greetings, and sounds of animals and nature. However, the second side is more intriguing. It consists of various tones, separated by audible beeps. These tones encode images and audio signals, where pitch corresponds to brightness values and timing corresponds to location. The intended display for these images is a classic standard definition CRT television with 512 lines of resolution, each lasting 8.3 milliseconds. Each image corresponds to 4.2 seconds of audio. As the record is in stereo, 2 images are played back simultaneously, with 2 streams of audio conveying distinct information. With the aid of modern digital technology, individuals such as Ron Berry have followed the instructions on the record cover, successfully revealing the concealed content within side B. This highlights the continued relevance of the encoding method, even in contemporary times. While the probability of extraterrestrial intelligence discovering Voyager is exceedingly low based on measurable standards, the success of Carl Sagan and his team in communicating remains uncertain. Nevertheless, the Golden Record functions as a model for future generations of humans to expand upon. The experiment's purpose was fulfilled not only by the transmitted record, but also by the innovative approach developed, a testament to the ingenuity and forward-thinking nature of the effort, scientific contributions, and future inspirations. The commencement of humanity's interplanetary exploration took shape with the success of the Mariner 2 NASA spacecraft, which carried out a historic flyby of Venus in 1962. This significant accomplishment marked the initiation of a new era in space exploration, laying the foundation for subsequent undertakings. Fast forward 27 years to 1989, and the Voyager 2 spacecraft conducted a crucial flyby of Neptune, concluding a remarkable chapter in the initial exploration of our solar system. Throughout this time frame, the human species achieved an impressive milestone by closely approaching, orbiting, or landing on each of the planets in our celestial neighborhood. This unparalleled exploration signifies a distinct historical moment, as humans extended their reach beyond Earth, dispatching both artifacts and themselves to unravel the mysteries of the local space environment. The privilege of living during this epoch is emphasized by the profound increase in our understanding of the solar system. Consider the remarkable shift in our understanding of the solar system. Objects that were once unknown or distant points of light have now undergone detailed study. Our comprehension of these celestial bodies, including their surface features, has seen significant revisions since the initial explorations. The Voyager and Viking missions, particularly from 1975 to 1989, played a crucial role in reshaping our knowledge of the solar system. As we explore the various worlds and 56 moons investigated by the Voyager missions, a notable observation emerges. There is no indication of life. While the formation of complex organic molecules hints at the potential for life, there is no concrete evidence suggesting life elsewhere in our solar system. This realization emphasizes the rarity and preciousness of Earth and the life it sustains. In February 1990, Voyager 1, positioned 40 astronomical units away, turned its cameras inward to capture the iconic image of Earth as a pale blue dot of light. This meaningful image served as a farewell glance at our home planet before Voyager 1's imaging system was powered down. The Voyager mission holds personal significance for many beyond those directly involved, resonating with individuals through childhood memories. As children, encounters with planets, particularly Uranus and Neptune, played a crucial role in shaping our understanding of our place in the solar system. The vivid images of these distant planets, shown on the evening news, left a lasting impression, conveying the excitement of human exploration to those born in the 70s and creating a shared sense of being among the first to witness these planets in such detail. The emotional connection to these celestial journeys adds a nuanced layer to the significance of this era in space exploration. Despite being the second spacecraft launched, Voyager 1 has earned the distinction of being the fastest and farthest traveling spacecraft from Earth. Currently moving through space at an impressive speed of approximately 38,000 miles per hour, it maintains a lead that cannot be surpassed. On the other hand, Voyager 2, though slightly slower at around 34,000 miles per hour, still travels at a velocity that is an astounding 40 times the speed of sound on Earth. Frequently compared to senior citizens, the Voyager spacecraft defied their age with remarkable resilience. Serving as twin sisters, these identical spacecraft have endured the test of time, each facing its unique set of challenges. Despite the gradual depletion of their nuclear fuel source and the resulting decrease in power output, both Voyagers persist as active entities. Throughout their remarkable journey, the Voyager probes have shown incredible resilience, overcoming challenges as they travel through space. Despite facing difficulties, some of the instruments and heaters on board were deliberately turned off over the years. Surprisingly, even in their weakened states, these probes continue to carry out their mission, diligently observing charged particles in the vast space around them. A crucial moment in the Voyager missions occurred when both probes successfully crossed the boundary between the solar wind and the interstellar wind. This noteworthy achievement, realized decades after initial predictions, reflects the enduring success and longevity of the Voyager missions. With an impressive track record of 44 years and counting, Voyager 1 now holds the title of being the farthest man-made object from Earth. Situated at an astounding 156.5 astronomical units from the Sun, this accomplishment provides a perspective that is truly awe-inspiring. 156.5 times the distance between Earth and the Sun, equivalent to a journey spanning 21.5 light hours. The lifespan of these spacecraft is expected to continue until they reach approximately 200 astronomical units in the early 2030s. Beyond their impressive astronomical feats, the Voyager probes have surpassed expectations, significantly enhancing our understanding of the solar system and the wider universe. The wealth of data collected throughout their journey, spanning from the mission's inception to the present, represents a profound contribution to the pursuits of both new generations of scientists and artists. Voyager 1 has presented a puzzling situation for NASA's scientists. Positioned at an extraordinary distance of 15.1 billion miles, the spacecraft's flight data system is transmitting binary data that seems unintelligible. The FDS, consisting of 3 onboard computers, is stuck in a repeating digital pattern, defying attempts to address the issue, including the standard procedure of rebooting. According to Andrew Good from the Jet Propulsion Laboratory, Susie Dodd, the Voyager project manager, assures the public that the team is diligently working to identify and resolve the problem. Notably, there were no warning signs preceding this unusual behavior. The main challenge arises from the vast distance between Earth and Voyager 1, resulting in a 22.5 hours time lag for messages to travel between the probe and mission control. This communication delay complicates the troubleshooting process. Despite the cosmic challenge, the team is carefully reviewing past documents and codes, taking care not to accidentally overwrite essential programming. Each attempt to fix the issue requires patience, as they must wait nearly a day to assess the effectiveness of their interventions. Both Voyager 1 and Voyager 2 stand as remarkable achievements, being the only human-made objects to breach the boundaries of interstellar space. Carrying the Golden Record, a compilation of images and sounds curated by Carl Sagan and Associates, these vessels symbolize humanity's enduring curiosity and creativity as they navigate the vast expanses of the cosmos.